What am I doing? Oh, I rubbed my eye. And I've been wearing, I'm wearing makeup, and I wonder if I messed my eye up. So I'm gonna have to look at my eye. Oh, perfect. I don't want to mess up my eyeliner. Okay. Okay, yeah, we gotta resume class. I'm a little bit late. Oh, I need to go get my drinks. Two monsters. Okay, everyone, react to the message in Discord if you are present. Show your presence using emotes of cats? I don't know. Looks like there's cats this time. Okay. All right. Let's resume. All right. We got this. This is the final planned lecture, and then the next one is going to be on Friday, and that's when we're going to do whatever topics you want to talk about. Might be esoteric topics, might be just other useful topics, whatever you prefer. That's going to be Friday. Wait, not tomorrow? No, I thought we only had Friday. Oh yeah, wait. Yeah, so Wednesday, sorry. Yes, tomorrow we're gonna have only assignments, but I'm gonna be available on Wednesday. So I'm gonna be available for basically the same amount of time as the lecture time. And then on Friday, we're gonna have the last lecture. So tomorrow is not a lecture, you're just gonna have assignments to work on. And I will be available for help throughout that entire time. Yeah, that's tomorrow. But Friday is gonna be the last lecture, and that's gonna be the mixed random topics. New assignments are the same ones. There's going to be new assignments, and you are welcome to work on the old ones as well if you want. Thursday, I'm not going to be available. You can keep working on the assignments if you want to. It's up to you. Ideally, you would work on the assignments. That's what I would recommend. I think my plan is to give you a large bucket of assignments where you can't possibly do all of them, where you just pick which ones you want to do. Like, if you want to learn more Trig, you pick that one. If you want to learn something else, you pick something else, and so forth. Are going to help through text or through Teams? I imagine I'm just going to hang around in Discord. We could do voice channels. I can stream in Discord. Yeah, I'm going to be available in this Discord that you're in. Friday, the last day of not having to deal with teams. Seems like there's like every group of students. None of them like teams. It seems like I haven't tried it out for my lectures, but it sounds like my option is better so far. Except the fact that it's public, which has downsides too. Okay. There's kittens. Look at kitten. Oh, salad. Oh no. Oh no. Salad. Hello. Salad is sitting on Ashley's computer. And then Toast is in the box. So it's a good box. Very, very good box. Kittens. Anyway, that's not part of the lecture. When's Krista gonna give us the assignments? I have no clue. I don't know how the like actual canonical graded assignments are gonna work. So I don't know. I would ask Krista, and I will. I mean, I can send Krista all of my assignments, and maybe he can turn some of them into required ones. I'm just not going to be available to grade and all of that kind of stuff. Yeah, and so that's up to Krista. I don't like grading stuff. I'm uncomfortable because I don't know if someone cheated or not. It's hard to tell. I don't know if you just copied or pasted or if you actually learned. So for me, I just want to give you the possibility to learn, and I want to be available if you have questions and just push you in the direction you should go if you want to learn things. That's my job. And then when it comes to the like formal requirements of assignments, I'm just leaving that up to Krista because I don't have that much time, and I don't want to do it, and so that's why, for better or for worse. But yeah, it's I don't think it's super. Yeah, I think it's mostly just for the formality because you have to, according to the school system. Okay. Are we ready to start doing new things? All right, I think we're ready. Whew. So, first there are two things I want to talk about that I didn't really cover last time. I'm just trying to say that I forgot to talk about them, so I'm gonna just talk about them now. So we talked briefly about the inverse trig functions. We had the arc cosine, and yeah, both of these are the arc cosine. Usually you type them as a cos or cos to the power of -1. So that's the inverse cosine. The inverse cosine basically gives you an angle given an x-coordinate, right? So if you have the x-coordinate of v, it gives you this angle right here. The problem, though, with the arc cosine and the arc sine, which is the opposite of the sine, so that is arc sine of some value x. The problem, though, is that it's actually kind of complicated to just go from a vector component directly to an angle, because there's ambiguity here, right? Like, it's kind of hard to know which quadrant you're in if you only have that one component, because if you look at this vector v, if you draw another vector here, then this one, what's ambiguity? Ambiguity is when it's hard to tell the difference between different cases. So in this case, if you have two vectors, you have one vector here and one vector here, these both have the same x-coordinate, right? So they have the same x-coordinate, and so we don't have enough information to know if we want this angle or if we want this angle, like negative alpha, right? And so we can't tell the difference between these two cases because both of these vectors have the same x component. And so when we were talking earlier about going from an angle to a vector, okay, I can't find that. So if you want to go from an angle to a vector, then you would do something like v equals, I'm going to do a column matrix because why not? Then the x component was the cosine of alpha, right? And then the y component was the sine of alpha. Just gonna erase that. So this is kind of how you go from an angle to a vector, right? And we use this in our code. So we had that in somewhere here. I believe it might have been in the trigger, or no, we had it in the clock. So that's this function right here. Angle to direction. We just use the cosine and the sine of the angle, and then we get a direction. But what about the other function? Like, what if you have the you want an angle, so you want to go from a direction to an angle. So you pass in a vector. So that's our vector v. So how do we do this? Well, there is a math function that is somewhat confusing. It's confusingly named and the parameters are confusing, but there's a function called a tan 2. So it is called a tan 2. It's a shitty name for a function, but it's called a tan 2. It's similar to the arctangent, the inverse tangent, but it has a bit of an extra thing that it does that makes it a little bit easier to resolve. So it basically resolves ambiguity. So a tan 2, we can use that to... wait, is there any difference between using a 2D vector instead of a 2D vector? What? Do you mean 3D? I'm not sure if you mean 2D versus 3D because you type 2D twice. So angles get a little bit more complicated when doing them in 3D because they, like, it's almost only useful to talk about them in 2D because all angles are in a plane, right? And so usually in 3D, you would just decide, okay, we're rotating around this plane, and then we're doing 2D math in that plane. So it's effectively just 2D, but everything can apply to 3D as well. Just a matter of picking which plane to work in. Yeah. Asking what ambiguity is and then typing that sentence is a massive struggle. That's true. Okay, so a tan 2 is a function and it takes a vector, or a little bit confusingly, it takes the y component of a vector, and then it takes the x component of the vector, and then it returns the angle. So angle equals a tan 2 of the y component and the x component. So this is basically the way to convert from vector to angle, and this is angle to vector. So these two are functions that I use a lot every time I do anything that involves like circular placement or movement or anything. It's super useful. And so these two functions are good. The confusing thing about a tan 2 is obviously that you're doing the y component first instead of x. This is weird, it's shitty, but it's just the way it is, because nothing is consistent and everything is garbage. And so it's just, you just have to accept that. The way that I usually just do this is that I make a wrapper for this function. So I make the function that I started typing in code here, where I just do return math dot a tan2 v.y v.x. And then I never use a tan2 ever again. I just use the direction to angle function. This is how I usually do it because I think it is way less ambiguous. There's no chance of mixing up x and y, and I just like it. What's the angle in reference to? It's always in reference to the x-axis. So in whatever space you define the vector in, it's going to be the angle relative to the x-axis. How to visualize atan? Well, it gives you an angle based off of a value, right? But it's complicated in this case because atan2 has two inputs. But effectively, given a vector, you can get an angle out of it, and it's always the angle to the x-axis. So this is the angle you're getting. So this angle alpha. And so the angle is going to be in radians, and on this side, you're going to have positive values, and on this side, you're going to have negative values. So it basically goes all the way to tau over 2, and then on the other side, it goes to negative tau over 2. So it basically covers the full turn in radians. It's just that it centers on 0 here, and then it goes to positive values on this side and negative values on that side. Those are the angles you're going to get out of that. When I use atan2, it just calculates it on the world, right? What if I want to calculate of something else? This is just like most of the functions that we're doing, they have no knowledge of space. If you use atan2 on a local space vector, you're going to get the angle relative to the local space x-axis. If you're doing it with a world space vector, you're going to get the angle relative to the world space x-axis. So it all just depends on the space of your input. The functions will follow the space that you give it, right? And so there's nothing like, they don't have any knowledge about space. And so it's just based off of what you pass into them. Okay. Yeah, I can do more assignments on Trig if you want. So the directional vector that we give into it has to be relative as well. Relative to whatever space you want to measure in, right? Okay. Maybe I should actually clarify this for the future. Because I'm guessing you're gonna want this whole sketch board after we're done, and if it contains more information, then that's valuable, I think. Just making some space. What do you mean empty? You're empty, Photoshop. Thor is screaming. Thor! So this is angle 2 direction. And this is vector to angle. It doesn't have to be normalized for this input. It's going to work regardless. Okay. There you go. Good things to remember. Again, I use these a lot, and I almost always make helper functions for them so that I don't have to type atan2. It's a confusingly named function with confusing parameters, but it's like that because it's historically been like that, and then people are very reluctant to change things. And so, yep. All right. Let's see. Okay. So that was one thing that I hadn't talked much about, that I should have covered in the trig section. The other thing is our dot product here. I wonder if we should maybe we're gonna copy these. We're just gonna steal them, I think. So we're gonna need them. Okay. Dot product. All right. I'm guessing you remember the dot product. We talked about it a lot. There's actually one, a little bit of a, so the dot product kind of has a hidden, lesser known sister that we rarely talk about. And it's kind of confusing as well because there are so many definitions for it, and there's no proper name for that function. But when you do the dot product between two vectors, like let's say you're doing the dot product between v and the x-axis, the dot product is, the result of the dot product is the cosine of that angle, right? Because as you can see, you're projecting v onto the x-axis. And because both of them are normalized, again, that's when we have the vector projection or the scalar projection. So the dot product is basically related to the cosine function, right? And so that's why you can define the dot product using the cosine, which is kind of cool, right? Like you have this like relationship to the trig functions, even though the dot product is simply just multiplying the components together, right? It just so happens that it directly relates to the angle between them, and that's kind of cool. But that kind of begs the question, doesn't it? Like, what about the sine function? Like we have the cosine here. Like what function would do this effectively, where you have the length of a, and then you get the length of b, like so, and then you have the sine of our angle theta. So what is this? Turns out this actually has a name. The problem is that it has too many names. Like it has a shitload of names. So this can be called the determinant. It can be called the perpendicular dot product. It can be called the 2D cross product, which is technically incorrect. And it can be called the wedge product. It can also be called the exterior product. It can also be called the antisymmetric product. Those are all the names that this function has in 2 dimensions. It is really confusing because it has so many names. As of late, I'm leaning towards calling it the wedge product. So I like the wedge product because it actually has a symbol, which is a little upwards wedge like this. It's mostly used in geometric algebra, but I think it's okay to sneak that into our regular vector math. So we have A wedge B equals this whole thing. Okay, I just need to bring up my notes because I always get the component order wrong when I write the other version of this. Math course. Where's my... There we go. Okay. And turns out the determinant, specifically in 2D, or the wedge product in 2D, can also be written similar to the dot product. We can use the components to write this. So we have B, wedge A. So this one can be written as A x times B y, and then minus A y and B x. There we go. So this is the wedge product in 2D specifically. This does not generalize to 3D. And so this is actually very closely related to the cross product. If you look at the definition of the cross product, it kind of looks like this for every component. And so if we go back to our cross product, you can see that we actually have the wedge product right here. And so the cross product and the wedge product are very, very related to each other. But the different definitions of the wedge product is actually, it just varies widely depending on which region of math you're in. But in general, I would call this the wedge product. Wedge product, or it can be called the determinant. Okay. So is the wedge product non-commutative then? Yes. Okay, so the wedge product basically gives us that lost other component of our vector. So the wedge product gives us the sign value here. And so just like the dot product, we use the dot product to tell like how similar are two vectors from each other, like in the unit circle, right? If we have a vector that's pointing kind of in the same direction, we have a value that's greater than 1, right? If it's pointing in the opposite direction, it's going to be, or sorry, not greater than 1. On this whole side, the dot product is going to be positive, right? Between this vector and some other vector. So it's going to be positive on this whole side, and it's going to be negative on this entire side. So the wedge product, instead of checking if it's in front of or behind, the wedge product checks left and right. So that's kind of how you can interpret that. So instead of checking this plane, it's kind of checking along the object itself, or along the other vector. So now if we use the wedge product, then it's going to be positive on one side and negative on the other side. And so here, you can actually use the wedge product to tell, like, for instance, if you have a car, like an AI of a car, and you have something you're going to drive towards, you can just check, is this thing to the left or to the right of me? And if it is, then we determine which direction we should turn. Is it always positive on the left? All of this depends on your orientation and coordinate system. I forget which side is which. It could be the other way around. There's a 50% chance No, there's a 60% chance I got this right. I think it's positive to the right. Yes, it should be positive. Oh, sorry, positive to the left. I'm 80% sure of that now. Okay, so this is kind of the lesser known sister of the dot product, which is very useful to know. Yeah, good to remember. Is this also in Unity's math? I have it in my library. I think they might have added it recently. I think they might have called it perpendicular or something. It might be in vector 2. Oh no, this gives you a vector. Okay, yeah, no, they might not actually have it. I don't think they do. Wedge product, determinant, no, they don't. That's why you should use my math library. My math library has it all. So you should check it out there. It's called determinant in my math library. Because that was before I started looking into geometric algebra. Now I want to call it the wedge product. Okay. Right. That was just one thing that I also forgot to cover. That's good to remember. All right. Okay. Trying to figure out if we should do a 10-minute break before we continue. Yeah, let's do 10-minute break. Now we can resume to like a normal break schedule. I think that would be good. Since it's non-commutative, which one out of A and B is the reference vector to which you're comparing direction? Well, it would just depend on, like if you have two vectors, I guess we can give them some color. So if you have two vectors, you have A and B. Pretend these are normalized. Like if you want to check which side they are of each other, then I believe the wedge product between A and B, I think that is going to be, I think that's going to give you a negative result. And if you do B and A, you're going to get positive. I think that's the way it is. I forget which one it is. But so, because B is to the left of A, or sorry, B is to the right of A, and A is to the left of B. And so that's why they give different answers. They're going to have the same magnitude. The result is going to be the same magnitude, but they're just going to have different signs, right? Yeah, and so similar to the dot product, if they are perfectly perpendicular, so if you have A and B, you're going to have a value of 1. Or negative 1 if it's on the other side. So it's going to either be 1 or negative 1. Yeah, and then it's going to start going back to 0 if they're pointing exactly in the opposite directions. So in the opposite directions, it would be 0. If they point in the same direction, that's also 0. So you can see that it's basically like the dot product, but it's rotated 90 degrees. And so that's why it's sometimes called the perpendicular dot product. Yeah. Okay. Should we do break? Should we do break? Vote. Break or not break? I don't know if we should resume to the normal break schedule. Have opinions. Okay, break. Okay, let's do break. 10-minute break from now. Goodness. Toast! There's some cats going on in the background. I don't know what's happening. I think there's a salad in the bathroom. They're talking to each other. Toasty, salad. I still have something in my eye. I had something in my eye ever since we started. After the break. It's really annoying. How's YouTube chat? Can I also do scalar projection with the determinant? Yeah, I mean it gives you a scalar result. So yes, it's just like usually that's not called scalar projection. Usually that's reserved for the dot product. And so if you say scalar projection, they're going to assume you mean the dot product. Yeah. But maybe you could call it the perpendicular scalar projection or something. Okay, I think the kittens are playing in the bathroom. Sometimes they like randomly run out of the bathroom. I've also found them in the bathtub quite a few times. I just walk into the bathroom and then there are two cats in the bathtub. Either just napping there or they're like wrestling and tumbling around. I don't know why they hang out in the bathtub. Salad! I can hear Salad. He's like chirping away. That was a yell. Boys, how you doing? There's some big wrestles going on. Could you hear that? I don't know if you heard that. I'm gonna see how they're doing. Boys? Hey! Hello! What's going on? What's going on? They were just lying on the floor. I'm guessing they were wrestling, but I don't have any evidence of that anymore, apart from the sound. Here come the boys. Hey boys. How you doing? Vloop. Just one snack and then vloop. Okay. What a good pair of boys. Okay. Okay. Okay, toast. Bloop, bloop, bloop. Okay. That's valid. These are two spots. Oh, toast collapsed. Oh no, toast, you collapsed. He's flat now. Is it toast? Because of the color markings? Yes. Because toast kind of has a toasted snoot. Tastes like a little bit of toasted bread. Yeah, it looks a little toasted. That's why it's called toast. It doesn't go any deeper than that. Yep. Can I notice salad is not green? Okay, so the name of salad was inspired by a tweet. This was inspired by two things. One is you know the meme with the two ladies that are yelling and pointing at a cat, and there's a cat sitting in front of a plate of salad looking great. That cat's name is that cat is called Smudge Lord. You should follow Smudge Lord on Instagram. Anyway, inspired by that, the salad cat, we actually have a canvas print of Smudge Lord over there. Anyway, so it's a cat in front of salad, so it's kind of funny. Anyway, and then the other inspiration for salad's name is from this tweet. I just love this tweet. It's a very good tweet. And so kind of from the result of these things, we ended up just naming him Salad. We considered naming him like bok choy, but it's a little bit like annoying to say every time. And there's something there's something endearing with the name Salad. Like, I just love it. It's really good. I kind of just said it as a joke. And then it kind of stuck. You just like joke like, oh, maybe we should name him Salad. Like, haha, that's a dumb name for a cat. And then it's just like, well, I actually kind of love it. So, yeah, and so it kind of stuck. And so Salad and toast. Heard of bok choy, but what we got here is some sort of chunk boy. That's the boy over here. He's the chunk boy. Yeah, that's you. That's you. Oh, you caught my Hello Boy reference. I'm glad, Nicholas. It's Salad. Okay. We should resume. Okay. A real bonkus chonkus. Just a real chonkster. Okay, we're resuming. Please react to Discord message. Specifically with cats, because we've been talking about cats. So you're gonna have to find a cat emote. I'm seeing 4 frogs here. What's up with the frogs? We're doing cats. There's some fake students that are reacting with frogs. The audacity. Okay. Where are we headed next? Oh yeah, we have a few more things about the determinant that's useful to know. Okay. So, there is another interpretation of the value of the wedge product that is actually kind of cool and it's actually one of those use cases that you use when measuring area, specifically for triangles. So if you have two vectors, you have a vector, we're gonna use colors. If you have a vector here, let's call this A. Then you have another vector, and then let's call that B. Very unique names, I know. Then one thing that the determinant or the wedge product actually represents is the area that these two vectors form with their parallelogram. So if you imagine A and B, if we just stack them onto each other like this, so this is B and this is A, then the area that they form here is the determinant between those two. And so that area is A wedge B, which is kind of neat, that we just kind of automatically get that area using the wedge product. So I should probably remove these labels. Okay, and so this can actually be used to measure the area of not only this parallelogram, but you can also use it for triangles. And so if you cut this in half, then you're going to get the area of this triangle, right? So it can actually be used when measuring. If you just want to get the area of a triangle, you can do that using the wedge product. And just dividing the results by 2, and then you get the triangle formed by the two vectors A and B. Now in 3D, it becomes a little bit more complicated, but we can use the 3D equivalent of this. The 3D equivalent would be, again, remember the wedge product is very similar to the cross product. And so if we want half of the area of something in 3D, then we would actually do the cross product between A and B, and then we would get the magnitude of that. And so this would give you the area of the parallelogram in 3D, and this would give you the area in 2D. If you want the area of the triangle, you would divide it by 2, because then you're cutting it in 2. So you can actually use this to calculate the area of a triangle in 3D, which is a neat use case. So this is triangle area in 3D. Oh geez, I didn't align this at all. It's fine, we don't have to align it. So this again is the triangle formed by two vectors. We have two vectors there, and then the triangle they form would be that area right there. I don't know how to draw straight lines. Okay. And then this would be the 2D equivalent. If you just have 2D vectors, you don't have to use the cross product. You can just use the wedge product or the determinant. And then you would get the parallelogram area. And so you just divide it by 2. The one thing about the wedge product, though, is that this can actually be negative. So it's not just the area, it's the signed area. So this is the... So if we do A... Because again, area is usually a quantity that can only be positive. But if it's signed, it means it can be negative. So if you take the wedge product between A and B and divide it by 2, you get the signed triangle area in 2D. Okay. So this would basically tell us if it's which direction it's kind of pointing. If the plane is defined counterclockwise or clockwise, this would give you the signed triangle area. If you don't care about the sign, you just want the area, you would just do the absolute value of this, right? It would turn negative numbers positive, and then you would just get the triangle area. But without using the absolute value, then you would just get the signed area. So just a thing to keep in mind. So these are neat little useful things. Okay. I think that might be it for the wedge product and the determinant. Oh, so it's called the determinant because it's kind of like taking the 2x2 matrix and arranging your vectors like this, where you have ax, ay, bx, and then by. And then you get the determinant of this 2x2 matrix. So the determinant is just an algorithm you use to get some properties out of a square matrix. So the determinant of this is the same thing as is this math right here. That's the algebra that you do when you want to figure out the determinant of this 2x2 matrix. So that's why it's called the determinant. Yeah. Okay. Do you want some use cases? Or how are you feeling about use cases? I'm not sure how much you want me to continue talking about other things or show things or... Yes, please. One yes. Okay. Okay. So here's a fun little math problem. Let's say that you have, we're doing this in 2D now, just for the sake of the argument. Let's say that you have a triangle. Creative, I know. You have a triangle, and there we go. Beautiful triangle. All right, here's a math problem. Commonly used in intersection testing to see if your cursor is at some specific place or whatever. This is a common problem. How do you test if a point is inside or outside this triangle? So if you have a point P, here's a point. Is this inside or outside? And then you have another point here. Is this inside or outside? Like, how do you do that? Like, what is the math to figure that out? Excuse me. And so here's a case where using the determinant can actually be kind of just give us the answer straight up. And so if you consider the vectors between the vertices here, you see this vector, right? And then you have this vector, and then you have this vector. It's kind of like three separate vectors. If we check the determinant between our points, so let's add a point here. And then we define the vector relative to one of these sides. So now we have a vector here. Then we can check which side is this point on. Is it to the left or to the right? And that's exactly what the determinant can help us figure out. If the determinant between these two vectors, if that is positive, it's to the left, depending on which order we're doing it in. And so we can check, okay, is it to the left of this vector? Yes or no? Then we do the same thing for the next one. Is it to the left or right of this vector? Yes or no? Is it to the left or right of this vector? Yes or no? And so once we've done that for all of these vectors, so then we can actually figure out, like, are we inside or outside? In fact, you can actually shorten this problem to just checking, is the sign of the determinant the same for all three? If it is, it's inside, which is kind of beautiful. You can just kind of use, like, you use the determinant 3 times, and then you can determine if you are on the inside or outside, which I think is kind of cute. So that's a use case right there. Did that make sense? Or do you want me to, like, implement it in code? Works for other shapes as well? Yes, it does. So this strategy of checking left and right works for any convex polygon. So in case you're not familiar with that terminology, a convex polygon is one where, so let's see, here's another convex polygon. How do you do with a circle? We've already done that. That is a distance test, right? And so if you want to do it with, you can do the same strategy for any convex polygon. And a convex polygon is a polygon where the internal angles, all of them are less than 180 degrees. If you have a polygon that has an angle that is more than that, so this one, here we have an angle that is more than 180 degrees. So this one is convex. So this strategy would not work for this one. Or sorry, this is concave. The left one is convex. So this is convex. And this is concave. Another way of thinking about it, if it's possible to draw a line that passes through the polygon more than once, it's concave. So there is no line we can draw that passes through this one twice, right? But for this one, we can actually do that. This line passes through twice, which is more than one, actually. And this definition works for 3D polytypes as well. If you can draw a line that passes through the shape more than once, then it's a concave polytype. Anyway, useful terminology. So this strategy of checking left and right only works for convex shapes. Okay, you do want to see it in code. Let's do it in code. All right. What a nice 24-hour clock. Does this apply to 3D shapes too? Yes, you can do this with 3D shapes. Instead of checking left and right on a line, you would do left or front or back of a plane, right? Okay. Triangle test. Let's create some points for a triangle. A, B, and C. Give them some labels. And then we want to set Z to 0. Okay. ABC. Wow. Then a new script. Let's just call it triangle testing. I guess we can just do, let's just call them ABC. That's the transform, not the position. So let's just do TF. Go back to our trusted on-draw gizmos. Then we need to define our points. So A equals ATF dot position. Then we do the same thing here. What? Okay, then we want to draw some lines. So gizmos dot draw line from A to B, and B to C, and C to A. That's gonna draw a little triangle for us. Well, if we assign the variables. All right, this looks like a triangle. I think we did it. And now we want to test if a point is inside or outside of this triangle. So we need another, a transform for the point. Let's just call that P for the point, or maybe PT. So PTF dot position. Then we want to draw a sphere at the point with some small radius. Okay. Let's see if that works. And we need to create our point. That radius is too big. Okay, it's kind of behind the label, but that's okay. We'll just hide the label. All right, now we need to make a little testing function. Is this inside or outside of this triangle? That's what we want to do. All right, so we're gonna make a function that returns a bool. Triangle contains. All right, then we have the vertices of the triangle. So A, B, C, and then we have the point itself. And we're just gonna set the gizmo colors based on this. So red if it's outside, and white if it's inside. So a triangle contains A, B, C, point, and if it is inside, we do color.white, otherwise we do color.red. Okay. So now we've just kind of isolated the math problem into its own function, which makes it a little bit nicer to work with. It isn't entangled up into everything else. Okay. So first off, we're going to need the determinant. It actually doesn't exist in Unity's library. So we're gonna do that. So public float, or let's call it wedge product. So wedge product is between two 2D vectors, specifically 2D vectors in this case. And then we return a.x times b.y minus a.y times b.x. And that's our wedge product. There we go. It has many names. It's too many names. Okay. And so in order for us to check if something is inside of this triangle, what we need to do is to check if it is to the left or to the right of each of these relative vectors, right? So what we have right now is the points here. We don't have the relative vectors. And so we need a function that can tell us where is a point, P, relative to the vector between two other points, if it's to the left or to the right. In other words, we could just return the sign of this. In other words, it can either be -1 or 1, depending on which side it's on, right? Or we can return a Boolean value, just true or false, depending on which side it's on. So now we need to figure that out. Like, how do we make a function that can tell us what side something is on? So we need these two vectors now. We have 3 points, but not these two vectors, because again, points are usually relative to some origin in world space, right? So we have some coordinate system somewhere. And so all of these are now relative to the world origin. And so we want the difference between these 2 points and the difference between these 2 points. So that's what we need to figure out now, in order to do this side checking of using the wedge product to see is it to the left or to the right. All right, so we need these 2 vectors. It might be convenient to turn this into a function, just getting like passing in these 3 and then getting a value for which side it's on, right? So we can just we can use integers of Boolean values. Either is fine. So we can do get side sign. Maybe that's the name of this function. Okay, so let's say we have names here. We have A and we have B. And we want the vector from A to B, so that is B minus A. And then we want the vector from A to P, which is P minus A. So we want both of these vectors relative to A. That's effectively what we're doing. Maybe we can do that outside. All right, so we have vector to A, vector to B, and then we have P. Okay, and then we have the side vector, so that's going to be B minus A. And then we have the point, but it's relative to A. So this is going to be the point minus A. So both of these are now vectors from A to those original points. And now we can use the determinant, or the wedge product. So the wedge product between the side vector and the point. This gives us a value for basically a scalar projection, but it's rotated 90 degrees. But in this case, we're not really interested in exactly what the projection value is. All we really need to know is the sign of it, right? Like, is it positive or negative? So we can just do return math dot sign. Oh, it returns a float. That's gross. Okay, well, if it's greater than 0, return 1, otherwise negative 1. Can squish that into a single line. Okay. So this function will basically return either 1 or negative 1, depending on which side P is on of the line formed by A and B. Okay. And so now all we need to do to check if a triangle contains the points is to check the sign for each edge of the triangle. So we have to check if get side sign. Actually, this is going to be easier if we return a bool. Let's just do a bool. Let's just do true and false instead of 1 and negative 1. So if the get side sign of A, B, and the point is on the same side as B and C, I guess we can do these separately. So we can do bool AB and then BC. So we have BC and then CA. So then if AB equals BC and BC equals CA, then we return true. That means that they are all on the same side. Just rename this to side since it's no longer a sign. Yeah, and this should be it. This should be all we need to do to check if a triangle contains a points. Now, I don't know if it works. It should work. I might have done something wrong. But let's try it out. Okay, so it's red, which means we're outside. And now we can detect if we're inside. Isn't that magic? We use the determinant to determine something. Isn't that cute? Did that make sense? Are there any questions about this? It'd be determining true. Is it important that the order the vectors compared to are in the correct order? Can you do CA equals get side AC, or must the order be CA? The order must be the same if we're going to compare it the way we did here. So yes, they have to be the same. Otherwise, you're going to flip the sign of them. So then you're flipping left and right. So if you instead use this vector, then you're flipping which side would be true and which side would be false. So you have to have a consistent winding order. This is just called a winding of a polygon. So you should consistently go in the same direction. But as long as they're all in the same direction, it's fine. If you reverse all of them, this is also going to work. It's just that all of them are going to be either all true or all false, depending on the winding. And so, but in this case, the whether or not these return true or false, if all of them are false or if all of them are true, the final test is going to return true. Because the only possible way that these return the same value is if the point is inside. So another way of thinking about it is, remember how we did the trigger? How we had these like different boundaries of like, it has to be within a certain height range, has to be within a certain distance, and then we kind of combined these constraints together, just like a Venn diagram. We're testing if it's inside of this circle and inside of this circle, then we're basically testing for this region, right? And so we're doing the same thing here, but instead of our triggers having a small like volume, the volume we're testing is the entire side here. We're testing if we're on this side at all, right? And then for the next one, we're doing the same thing, but we're testing for this entire side. And so the Venn diagram, they only overlap in this specific triangular region. So that's how we're doing that test. Yeah. I suppose they can't all possibly be false at the same time. They can be. It depends on which side is false or true. I actually don't know which side is false and true in this case. As in, it could be if to the left is well, the only case where like if to the right is false, then it's possible, right? Because then the condition is that all of them have to be false in order for them to be inside of the triangle. I don't know which it is, and this function is actually agnostic. Whichever winding order we're using, this is going to work. So we can do clockwise or counterclockwise, but this function is going to work regardless, because it's just testing if they have the same Boolean value. It's not testing if all of them are true. Yeah. So we want an infinitely long triangular check. You can just remove one of the vectors. Yeah, if you remove one of these edges, you're basically testing for this region here, like an infinitely long cone, right? Yeah. Okay, so that's just one use case of the determinant, checking if something is inside of a triangle. This is very helpful and useful sometimes, if it's just checking if something's to the left or to the right of something. Okay. Let's see. Must have missed something. You're doubling up each of these tests. You're doing 2 get side tests for each A, B, B, C, and C, A. You only need 1. If that makes sense. So these lines are the ones that are different for us. Okay. All right. Okay, let's see how we're doing on time. So we are, because we're coming up on 15 soon. I feel like time just runs away from us rapidly every time. Like we never have time to talk about things. Okay. What do we want to do next? So we can go either frame rate independence and point physics, Or we can start talking about interpolation. We've sort of already talked about interpolation before, so we could... I'm not sure which... Frame rates. Okay. 1 vote on frame rate independence. Frame rate independence, interpolation, how do we feel? Interpolation, now we have two different votes. 1 against 1. 2 votes for frame rate. Physics, that's part of frame rate independence, yes. Okay, looks like we're going toward frame rate. Let's do frame rate. Okay, all right, frame rate independence. Let's disable that. I guess we can keep it enabled. It's allowed to hang around. So here's a neat little use case that we have in our project here. So we added the feature to be able to look around, right? But we can't move at all. We can't move the camera. It's all just kind of standing still. So maybe it's time to make it so that we can move the camera. And we probably want this to be in some sort of frame rate independent manner, right? We don't want it to move like at different rates on different frame rates. And so frame rate independence is all about making sure that your math is consistent across different frame rates. So just to set up a simple example, let's create a cube. Let's put it somewhere. Oh, I don't have a mesh on this cube. It's a headless cube. Cube. Beautiful cube. Okay. So let's say we want this cube to move. We just want to move it. We want it to move when we press play. So let's make a script called cube mover. What? I did not mean to lock my computer. Okay. So maybe we want this to move and update. Okay, so what do we want to do in update? We're going to move this cube. And what is movement? That is when you change position over time. So we're going to do transform.position plus equals new vector 3. Which axis do we want to move on? X-axis seems great. So let's say we give it a speed, and we set this speed to 1. That's our initial value. So we're moving it at speed along the x-axis. Every frame, because update is run every frame. And so now if we go to Unity and press play, this cube is actually gonna just fuck off to infinity very quickly. See, it's just yeeting out of the frame. So yeah, by cube, it is extremely far away, and it just rapidly disappeared. And so a weird thing that we've done here is that this is actually moving 1 meter per frame, right? So when we just do this and set speed to 1, this means 1 meter per frame. And so if you imagine, if you are running a slower computer, so we can actually check frame rate, I suppose. Okay, so I have 220 FPS. And so this one is going to move 220 meters per second, which is very fast. But if we had a slower computer, Or if we get a frame rate hitch, like maybe we're rendering a particle effect that's very expensive to render, then you're going to get a lower frame rate. And so we don't want the frame rate to be, we don't want this movement to depend on the frame rate, right? Oh yeah, I guess we can simulate that. So if let's see if we can simulate 10 FPS. Forget if I have VSync on, then it's not going to work. And there we go. So now it's moving slower, right? It didn't just immediately yeet off to infinity. This time it's kind of slow, because now we reduced the frame rate to 10 FPS. And that's bad. Usually you don't want movement to be like relative to your frame rate, right? And so the solution to this is something called just frame rate independence. As in, we want our movement to be independent of whatever frame rate we have. And so usually when we define speed, we don't want to define it per frame, we want to define it per second, right? And so a way to do that is that we can multiply our speed by the time difference between the previous frame and the current frame. And that time difference is called delta time. So we can call it dt. So that is, you can access that in Unity. It's in time dot delta time. And so if we multiply our speed by delta time, what we're going to do is that this will interpret our speed value in terms of per second instead of per frame. So now we're doing 1 meter per second instead, because we're multiplying by the delta time. And so now, if we go back, look at our cube again, press play. So now it's moving exactly 1 meter per second. You can actually see the position ticking up as if it's a timer, because it's 1 unit per second. We can also change the speed. We can change the speed to 2, or maybe -1, or -7. And you can see that it adjusts accordingly. So now it's going to be 3 meters per second and so forth. So time.delta time is a super important concept. Oh, and we should also test this on the other frame rate. So if we lower our frame rate, we should be seeing the same speed. And there we go. The frame rate is much lower, but it's still moving 1 unit per second. Okay. This is the same as just setting x to time.delta time, correct? Yes. If speed is a 1, then yes. Okay, this is a topic I'm interested in because when I moved object with velocity and fixed update, they use time.fixed delta time movement becomes incredibly slow and jumping no longer works. Right. Yeah, so you have to be careful about where you insert delta time. So the point where you have to insert it is when you are changing a position based on a velocity value. This is actually more similar to velocity than speed in this case. So it's specifically for velocity values, or rather, when you are adjusting it based off of, you're adding something to it, to a position based on a velocity value. Okay, but now we need to generalize this to 3D. This is just a one-dimensional movement, right? But what we want is, we want to be able to move a camera, right? And this is a good time to talk about what is velocity. We haven't actually covered that. So velocity is very similar to just the concept of speed, like how quickly is it moving? But velocity is kind of like, just like the dot product or just like vector coordinates. we might want a way to tell what direction is it moving and how quickly is it moving in that direction. And so usually when you want to have a value representing where something is moving and how quickly, that is always done with a velocity vector. Well, almost always, I guess. So usually a velocity vector is just an arrow. And so this is the vector, and let's call it v for velocity, and the speed I can't type anymore. Or write speed. Speed is the magnitude or the length of the velocity vector. So speed is always positive. And then obviously the direction you're moving in, let's just call it direction, is the normalized velocity vector, right? That's the direction vector. And so you can always kind of decompose your velocity vectors or any vector into its magnitude and its direction. And so this is kind of the way to interpret velocity vectors. And what this means, like how you can visually interpret this, is that if you have a cube at some location, let's say this location, if this is its velocity vector, then the tip here is where that object is going to be in 1 second. And so if you have a higher velocity, if the arrow is pointing like much further away, the cube would move over here in just 1 second, right? And so the longer the velocity vector, the faster you're moving. And so that's kind of how you interpret the velocity vector. Now, this is assuming it's going to be in the same direction as speed across that whole time period. Quite often the velocity vector is changing. And so really what it is just the instantaneous rate of change. The instantaneous rate of change is also sometimes known as a derivative. And so if you have a function that represents your position, the velocity is its derivative. So it's the rate of change of your position, right? Yeah, that's the velocity vector. And so the velocity vector is something you can like either write on your own, or you can get it from like Unity's rigid bodies. So if you have a physics object in Unity, you can actually access the velocity vector directly. You can also set the velocity directly in the rigid body. So if you have a rigid body, that's a physics object in Unity, so you can just access velocity directly here. And velocity is a vector 3 because it's a vector. Again, the magnitude of the velocity is the speed, and the direction is the direction you're moving in. All right. So yeah. So what we need to do is now simulate a velocity effectively. And what we want to do is we want to add movement to our camera so that we can press keys to move the camera, kind of like an FPS control, except it's a flying camera. And so where's our camera, right? When we press forward, we want to move in the forward direction. When we press left and right, we want to move along the x-axis and so forth. Break already? I feel like we just had a break. Okay, yeah, I guess we are on break time. Yeah, let's do break, and then we'll implement this after the break. Okay. I guess I can add some clarifying notes while we're on the break. How would I visualize this without using like derivative terminology? Mid-explanation? Not really mid-explanation. The next thing is to do code implementation of this. So it's not a bad break time. Okay, I'm gonna use some cursed math notation. Wait, you can see Omega Lol behind me? Oh, the the cat tunnel. Should just write larger things or use a smaller brush. Yeah, we're on break right now. Just in case you didn't know, we're on break. Yeah, break. I'm not just silently doing this because I didn't want to talk anymore. Yeah, resuming at 1500. Do you know a way to make Cinemachine cameras frame rate independent? I've never used them, so I have no idea. I think it's illegal to use the delta here. Like this. It might work because we're specifically doing it on a per frame basis. I'm not sure. Guess I'll clean up the notes while we're on break. Let's color code things. Why not? Randomly speeds up, down, jumps from location to location. That sounds incorrect. I'm guessing it's not Cinemachine's fault. It's got to be the input data you have to Cinemachine, right? Or like how you're animating across them. I actually have no idea how Cinemachine works. I don't know if it's like you have a camera with various smoothing settings, or if it's like animating along a path, or like what the situation is. It could be that you have like conflicting things. Like maybe you have both a smoothing algorithm, but you're also setting its position, and then you have like two conflicting systems trying to control the camera. That's what I would guess if it's from your description, but I don't touch any of that. Cinemachine does that. That's what I would imagine, but I'm guessing Cinemachine is not just completely broken and useless for everyone, right? It's a free look camera. Weird. I'm not sure. I have not used Cinemachine. I should go to the bathroom. What if it's something related to you're trying to set your camera in world space, but then you're also rotating the parent of the camera, and so like you're rotating the parent and then it snaps the next frame, and so you have this like one frame jitter, like a little discrepancy between something like that, maybe if you're getting like a very, very short frame jitter. I don't know. Camera has no parents? Gotcha. Anyway, we're resuming. Okay, we're resuming. React with cats. Has to be a cat emote, otherwise your presence is invalid. Reacting with tired salad. Okay. We don't have any toast emotes. I feel like that's sad. We have Thorn, we have salad, but there's no toast. Okay. So another way of looking at how motion works when it comes to physics like this is that we can kind of define velocity as the rate of change in position over time. And so this symbol here is called a delta. So this kind of signifies what velocity is. It is the change in position over time. And that's velocity. And we can actually go one step further. We can do the change in velocity over time. Actually has a name. This is called acceleration. So acceleration is the rate of change of velocity, and velocity is the rate of change of position. And you can keep going. Like these are all derivatives. So velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. And so this is a very basic relationship, and it's kind of intuitive when you're dealing with like physical objects that are moving. And so what we want to do is that we want to add a way to control the velocity using our keyboard. And so we're going to have to deal with velocity vectors now. So we can start out with modifying our little cube. So currently we just had one parameter called speed. But that was a lie, because this was actually a one-dimensional velocity vector, because we could make it negative, right? Remember, speed is the magnitude of the velocity. And so we're going to change this now to a vector 3, and we're going to call this velocity. Can just start at 0. Why not? And so now instead of just multiplying one value, we're going to multiply the entire velocity vector by delta time. Okay. But what velocity basically is, it's meters per second per axis, and it's a signed speed per axis. That's kind of what the velocity contains. And you can do a lot of stuff with velocity. I think I mentioned it briefly before that I've used the dot product between the velocity and the normal of a surface to figure out how loud should a sound effect be when you're hitting the ground. And so you can do a lot of stuff with this vector. It's very useful. What was the triangle? The triangle is called delta. It is just a symbol that means change. So change in position divided by change in time. That's kind of just the notation for that. Sometimes you also write it as d, so a lowercase d divided by dt. So there are different notation for derivatives. There's one that I like, that I use a lot in all of my stuff. You can also use a notation where if you imagine p being a function, so the position as a function of time, this is t. This is usually how I write functions. I don't know how much we should talk about functions in general. But if this is a function representing the position over time, then velocity is basically the first derivative of that function. And you can denote that with a little apostrophe there. And then the acceleration would be, so p and then a double tick. So that would be the second derivative of that function. Yeah. Just different ways of writing it. Technically, if you're a nerdy mathematician, all of these are technically slightly different, and I'm sure someone in YouTube chat is probably yelling at me right now, and I'm going to ignore them. But basically they're kind of the same. They all mean the same thing. But I guess position right now is not really a function. It's just something that happens. We have it in the world, right? So it's not really a function in this case, but But if it was, we could have used this notation. All right. And so we're now using velocity instead of just a single value. And we're multiplying it by delta time to make sure that we get this in meters per second and not meters per frame. So now we have the entire vector. And so if we wanted to move upwards, I'm going to press play. We set the y component of the velocity to 1. It's going to move 1 meter vertically per second, right? We can set x to 1 as well. Now it's going to move 1 meter per second on both x and y. Yeah, we can set y to a negative value, or we can go back to a positive value, or a lower value, like 0.1. So it's sloping slightly upwards, or -1, and it's going down again. Or we can negate the x-axis. And so the velocity vector is effectively just an arrow pointing in the direction it's headed. We could actually draw the velocity vector directly. So gizmos dot draw array from transform dot position, and the direction, or the vector, would be velocity. So we're visualizing the velocity vector. Okay, let's do orthographic. All right, 1 on the y-axis. Where's my gizmo? Oh, it's probably, oh yeah, it is there. It's just pointing along the y-axis. So there we go. That little white line is the velocity vector. So if we change it and move that direction, you can see that it strictly follows the same direction as that line, right? And if it's long, it moves fast. If it's short, it moves slow, and so forth. So that's the velocity. Okay, does that make sense? It's a vector representing the movement of this object over time. It makes sense. Okay. All right. Cool. What a velocity vector. So now we want to do something a little bit more advanced. We want to be able to move the camera using our keys. And actually, maybe we can start with the cube. Maybe that's a little bit easier. And then we can move on to the camera. So our cube is going to be our little testing ground. Okay. So velocity is now no longer just going to be a constant. We're going to want to press keys on the keyboard to set the velocity. And so we're not going to make that public anymore. So now we're going to add some input. So we're going to start with a very basic type of input. So we can do if input dot get key. And if we are holding, so let's see, W. So W in this case should be upwards, right? Along the y-axis. So if we are holding W, we want to move upwards. So we're going to do velocity plus equals vector3 dot up. We're also going to reset velocity here, just so we don't continuously add to it. So we reset the velocity, and then based on our input, we add vectors to it. So we can do the same thing here for the other key. So S would be down, and then for key code dot A would be left. And then D would be right. Okay. So this is basic input. So now we're setting the velocity directly based on our keys. And now if we go to, oh yeah, we're still drawing velocity. That's good. Let's recompile. Let's test this. And now I'm pressing keys on the keyboard, and you can see that we have this little velocity vector here, right? This tiny little white line. Now I'm moving upwards, to the right, and so forth. So that's our velocity vector. You might have noticed a classic problem when you're doing this type of input, and that is that you're moving faster diagonally, which might not be what you want depending on the type of game you're making. So you might want to make sure that the diagonal movement isn't faster, and so you might want to normalize that vector if you're going diagonally. And so the reason for this is because we're just adding up and left, for instance, and then the magnitude of that vector is going to be like 1.41 something instead of 1. So we might want to normalize the velocity here. Chebyshev approved? Yes. Again, in some cases you want faster movement along the diagonals, but quite often you don't. And so now we've normalized this one, so now it works fine. It no longer moves faster diagonally. So now it's always 1 meters per second in speed, regardless of which direction we're moving in. Okay. So far so good, right? Any questions so far? Oh, so we might want a parameter to like affect how quickly we're moving, because now we're moving pretty slowly. So we might want a value for how fast the movement should be, right? Player speed. Wait, why did I get a Slack notification? That was on my computer, so don't worry. That's not yours. Aren't many source engines using this a Half-Life and Counter-Strike, like when you bunny hop in those games? Oh, no, it's not directly related to this as far as I know. It's more about details of how they handle friction and how they use the dot product, actually. So if you just search on YouTube for like bunny hopping math, then I'm sure there's a good video out there that can explain why that bug exists and why you can bunny hop. It's a fascinating little glitch that kind of changed games for a long time. All right, so if we define player speed, then all we need to do, again, because the velocity is normalized, when you have a vector that's normalized, multiplying it by some value sets the length to that value. So we can just multiply by player speed. And so this would now be in meters per second. We might want to default to 1. Okay. Let's try that out. Okay, we have our cube. We can move slowly. And then let's change the speed to 5. So now we can move much faster. And you can see the velocity vector is now much longer as well. So that's some better player movement right there. Okay, I hope that made sense. Was there anything about this that was a little bit complicated? Or do you feel like this makes sense? Excuse me. Typing. Felt pretty self-explanatory. Good. Okay. Can you explain fixed update? Do we need delta time in that? So fixed update, it's kind of in the name. Fixed update is the separate update loop. So update is every rendered frame. So every frame that we're drawing to the screen. Fixed update is every physics frame. And in Unity, and in other game engines, I'm sure, the update rate of the physics engine is actually separate from the rendering update rate. And fixed update is usually a specific number. Like fixed update is defaults to 50 FPS is the default. And so when you're dealing with physics in Unity, the physics engine will only update at 50 FPS. But even if your game is running at like 100 FPS, your physics update is only going to be 50 FPS. And so the question of like, do you need delta time in a fixed update? Generally no, unless you're going to change this number. If you change the target frame rate for fixed updates, you will actually need to add delta time in there. So it kind of depends. If you're going to change the physics frame rate, then you probably want to add delta time there. Fixed updates shouldn't fluctuate depending on your computer. I think it should always be 50 FPS. I think there might be some caveats there. I forget what happens if it's like catastrophically slow. I'm not entirely sure. I don't remember what Unity does in that case. It might just halt update entirely and wait for physics to be done. But yeah. And so fixed update is generally consistent. But keep in mind the fixed update does not update as often as update. Generally, if you're making a game that's above 50 FPS, then update is going to run faster than fixed update. This number, you can set this number in your project settings. It's just a number, except it's in you set the delta time. So the default is 0.02, which is 50 FPS. But you can set this to whatever you want. So if you remember the rocket game that I showed you, where you like slide around these curves, in that game I have it set to 1 millisecond. So this is 1000 FPS. Because in that game I need ridiculously accurate physics because I'm dealing with very, very, very high velocity objects, and I only have one physics object, so I can actually just use all of that processing power for the one physics object I have. And because it's 2D physics, so it's cheaper than 3D physics. But most games tend to just stick to these. Sometimes you make it lower if you really have to optimize, but the default value is fine. And even though the frame rate is lower, the rendering frame rate is going to be higher, and physics objects can actually interpolate. So you blend between the previous position and the next position, even though you don't actually update at that frequency. So there are interpolation settings in rigid bodies if you want to set that, which is helpful. Okay. Should you use fixed delta time just in case? It's probably good to do that, but I think most people don't. I think most people don't care. And I think I'm also one of most people. In most projects, you don't change this. And so generally, you're going to be fine. Yeah. And usually the only things you should touch in fixed update is physics. You rarely touch something else there. What is late update? Late update is an update function that is called after animations are applied. So it's just later during the same frame. So it happens after all of the update functions have been ran. And after animations are applied, that's when late update kicks in. So if you want to do something like IK, so you have a character that's doing some animation or some pose, and then you want to adjust their hand to like fit some object, to like hold a can or whatever, then you can do that adjustment in late update. So then during the next update, it's going to animate to the next frame, and then your hand adjustment is going to kick in. So yeah. Yeah. I heard somewhere that all calculations should be done in fixed update. Is this wrong? Yes, that's wrong. Yeah, no. Like, update and fixed update they have different use cases, and you should put the code that belongs in update, and the stuff that belongs in fixed update, Yeah, it just depends. Are you touching physics? Use fixed updates. Is it just an impulse thing and it's something that has to visually update with every rendered frame? Then you use updates. Yeah. Okay. I can talk about this a little bit more. If you want, after today's class, I can stick around for a little bit longer and show how I use this in my game. If you're interested, but we should do that after class because we have a few other things we need to talk about before we end today's class. All right. Anyway, so we have every rendered frame. We're doing this. Okay. So one thing we might want to do, because right now the movement is kind of the movement is kind of like simple. We just set the speed or the physics immediately, and it doesn't have any smoothing at all. It kind of lacks like flow and personality. Like sure, it's instantaneous, which is like feels snappy, but sometimes you might want to have some amount of smoothing, right? Because now it's very not smooth. And so maybe we should deal with acceleration instead. So maybe player input should set acceleration, but velocity is a calculated value based on that. And so let's do that instead. So now we're gonna add another one called acceleration. Actually, let me commit this code first. So that you have this code before I add acceleration. That was the direction to angle. Then we have the triangle test. And then we have the cube. Okay. Okay, pushed it to the repository. Can we lerp the velocity? Yes, we will get to that. Spoilers, jeez. Actually, we can do it without lerp in this case, so it's not that much of a spoiler. What's considered physics is manipulating a rigid body physics, for example. It can be. If it's just a single impulse, like you have a weapon, and when a bullet hits an object, you want to add an impulse to that. That impulse just has to be applied once. It's not something that's continuous over several frames. You should use fixed update when you're dealing with continuous forces, like continuously updating something related to physics. Like if you've written code for floating objects, like you're adding buoyancy to objects, then you would put that code in fixed update because the buoyancy force is applied. Like if something is floating in water, the force you apply upwards is going to be in fixed update. That's where it should go. Because that matches the physics engine. Okay. Right, we're going to add acceleration to this. So now we want the player to modify the acceleration instead of the velocity directly. And so we're now going to do change velocity here to acceleration. And then we probably want to draw both of these. What colors do we use? Velocity was my red, and acceleration should be blue. Okay. I don't have my brand colors here. At some point you said Lerp technically never reaches its goal since it always goes a certain percent every step. Because of floating point inaccuracy, won't the float eventually get evaluated to its target value? Yes, I also mentioned that when we talked about that the last time. Okay. So player speed is now not going to be meters per second. This is the player acceleration magnitude. I don't know if there's a name for the magnitude of acceleration. I had never heard of that. But this is now meters per second squared. Okay. So we are now setting the acceleration, but we have to set velocity somehow. So our acceleration should now add to the velocity. So we're going to do velocity plus equals acceleration times time dot delta time. I've actually forgotten. There might be a factor of 2 here that you might have to apply. I forget. But this will work regardless. It might just not be mathematically accurate. Just a heads up, but it's going to work. So now we're modifying the velocity based on our acceleration, that is from our player input. And then we move with velocity the same way we did before. Okay. All right, let's see if this works. So now you can see that we have velocity in red, and the cyan vector here is the acceleration. That's the input. So this is now, my acceleration is now based on my input, and the velocity is just whatever happens based off of my input acceleration, right? So now it's a very sluggish moving thing here, and it actually never stops. The velocity is just like we're moving in space. So now we've basically created rocket thrusters. If we're moving a spaceship and there's no friction whatsoever, and it just continues forever. And so this is rocket science. That's the basic stuff, right? But we probably want this one to slow down a little bit, because now it's kind of weird if it's floating forever and you don't want to like slide around on ice all the time. So then we need to add some sort of dampening factor to this. And so here's where we can do it in many different ways. We can either do the physically accurate, really complicated like integration, or we can use Lerp smoothing and call it a day, or we can actually do it in fixed update and it's going to be consistent. So there are many different ways we can do this. I don't know which one we should do. We've done Lerp smoothing before. Maybe we can do the fixed update method now. So we're going to do dampening in here. So we're going to need a dampening coefficient. Or we can call it drag. And let's see. Do we want it to be divided by... I'm not sure if we should divide or multiply, but either will work. So dampening, in here we do velocity. We multiply that by the drag. Pretty sure division is what you're supposed to use for specifically for drag or friction like this. Okay, so this is our movement dampening. All right, and I think this should be somewhat valid. Let's increase our movement speed and set our drag to 2. That's our drag coefficient. Let's see if this works. Okay, I feel like our drag is way too strong. This is just aggressive. We basically can't go anywhere. So we want to set this to something else. I think 1 is turning it off, basically. So we don't want to turn it off completely. But then we can basically just tweak this until it feels good, right? I think we probably want, usually if you want a nice game feel, you want a very high input magnitude. And then you also want a pretty high drag. You want the like easing and the stopping to be pretty short. And so we might actually, 2 might actually be an okay value, but we just have to increase the magnitude by a lot. So this is not too bad. Maybe let's try 400. This feels pretty snappy and good. Like a little arcade mini game, right? But it's still smooth. It's a very, very short smoothing period, but it is smooth. You can change the drag coefficient a little bit more. Maybe a little bit more smooth than that. And so there we go. So now it's a little bit more slidey. Isn't that cute? We can just slide around. Our velocity vectors are pretty long now. But that's okay. We don't judge long velocity vectors. Okay. So now, let's see, 400 and 1.6 turned out to be nice values. The one downside of setting it up this way, of having like the magnitude and a drag coefficient like this, is that top speed is just implicitly defined based off of these. I don't remember how to calculate top speed, but top speed is going to be determined by the drag and the magnitude and how they kind of interact with each other. Just keep that in mind, that you can't really set the max speed directly. It's just kind of implicit based on how much drag is able to fight back the magnitude you add. Okay. All right. Maybe have drag at like 0.5. Yeah, that would cause it to accelerate because we're dividing by drag. If we multiply, then 0.5 would be slowing it down. Yeah. All right, I think we are ready to add this to our camera, right? The goal is to move our camera, not move this little cube. So now we can just port this to the cube. Let's also commit this code. So now we've acceleration-based cube movement. All right, time to do this on the camera. There are a few things we can do to clean this up a little bit before we continue. So I like to structure this a little bit differently. So usually I make a local function. For the key and the direction. And then I basically shove this in there and do key and direction. And then we can shorten this code a little bit. So instead of doing if input.getKey, etc., we can just call test input. And then we pass in the key there. And then we also pass in our direction. So now we've kind of compressed this code here. I think this is a little bit more readable. I like doing it like this. Yeah. Okay. We could also do another thing here, because if acceleration is 0, we shouldn't add things here, right? So if we can check if acceleration is 0 here, right? So we want to make sure it's not 0, and if so, we want to add it. Defining a method inside a method. Yes, this is called a local function. So you can do that. So it's very useful. Seems illegal. It's not illegal. Fun fact, it was actually my girlfriend that implemented local functions in C#, because she's a compiler engineer. I mean, right now she's working in game dev, but she implemented local functions as a language feature. All right, so now we have pretty clean code, and now I think we can port this to our camera. So where is our camera code? We have a lot of turret placer. That's the camera. All right. So let's see. We want to do things in updates, so we're going to make a function. Casually passes a revolutionary change as a fun fact. I think it's a fun fact. I'm so used to it at this point. But yeah. All right, so now we want to do movement of the turret placer camera. What do we call this function? Update movement. And then we also need a fixed update. There we go. And then we need some variables. We need the velocity, and we need the acceleration. Oh yeah, you don't specify type. Let's just call it the vel for velocity. Which other fun facts are you holding back on us? I don't know. I've met Gabe Newell. We had a conversation. It was really neat. I worked from Valve's office twice? 3 times? I forget. I've turned down a job offer from Valve. I've turned down a job offer from Unity. Ashley also worked on Firefox. She's a compiler engineer, so she worked on the JavaScript engine. What other cool random industry facts are there? I don't know. I don't remember. But there you go. Random facts about the people and companies you are aware of. Right. So we are copying our code from the cube. And we're copying it into... I did not invent math. I can tell you that. I did try to invent my own spline. And I did, but it's not a very good spline. And so I kind of went back to the drawing board with that one. I have so many things open. Okay, turret placer. There we go. Now we're organized again. Right, so we had our public values for movement. Let's see, so we might want to organize things a little bit better. So one thing that's super useful, I don't know if you've used this in Unity, there's an attribute called header, which will organize your inspector a little bit. So this one is gonna, you can just kind of categorize things. So we can do the same thing for like movement parameters and whatnot. Chebyshev was Freya in disguise. Oh no, what if Chebyshev was like a really problematic person? Oh no. What values did we use? It was like 400 and 1.6. Yeah. Okay. That's our default. All right. Update movement and fixed update. We just slap things in. We're copying over our movement dampening. We rename that to vel instead of velocity. And then we just slap in this into our movement code. Just straight up copy paste. We're stealing code from ourselves. Okay. There are a few things we have to tweak though. But this is a starting point. So we put everything there, and let's try. Let's see if this works. We can disable the cube because we're not going to do that one anymore. And let's go. Okay, we can look around and we can move up and down and left and right in world space. And so our directions are not the best, right? Like I feel like this is not quite the FPS controls we were wanting, right? And so we need to fix our directions. Our current directions are not great. And so we can just like sort of like think, what do we want to happen here? When we press W, do we want to move like directly along the camera's forward vector? Or do we want like forward but flattened to the ground like an RTS game? That kind of depends. But in this case, let's do FPS controls. World space FPS controls is the future. I hope not. Okay, so for our test input here, we're going to want to use transform.forward. For back, we're going to use or negative transform.forward. And for left, that's going to be negative transform.right. And for right, it's going to be transform.right. And a nice thing about this type of input test thing is that we can actually just add like some more if we want. What if we want to add like a space to move upwards? That is actually a world space movement usually. So then we can do vector3.up. So now it's kind of like the jump key. Can also do like a crouch key to move downwards. Left control, please. Thanks. Vector3 down. Press space to ascend. Exactly. All right, and that should do it. Let's recompile. Press play. And we now have some sort of FPS style control. We can use space and control to crouch and move around. Isn't that cute? Isn't that neat? Why no vector.left? There is a vector.left, just not transform.left, I think. Yeah, and that's it. Isn't that a neat little turret? What else? Oh, it was actually, I don't know if it's visible on stream, but there's a 1 frame discrepancy. The turret is kind of fuzzing around. It's like 1 frame behind. And I believe that's because we do the camera movement last. So we're placing the turret, then moving the camera, and then we render. And then we're placing the turret, moving the camera, and then render. And so I think what we want to do is we want the movement should go before we place the turret, because that depends on where we are and where we're looking. So we probably want these two to go early on. So then we shouldn't have those like frame rate issues anymore. So let's try that again. And so now it's all smooth and good. I don't know if that was noticeable on stream because it's a per frame thing. But now it's no longer fuzzing around. It's completely stable. And then you can still do the rotation thing. And zoom in the viewport, apparently. Okay, it does look better? Okay, good. Yeah, I wasn't sure if that was going to be visible. Missed that last part. What'd you fix? I moved the turret placement should happen after movement and looking. That was the important part. Because rendering happens after updates. So after all of the update loops have run, and then I guess all of the late update is going to run, and then the cameras render. And so we had this like discrepancy where we placed the turret, then moved the camera, and then rendered, which means the turret is always going to be visible at kind of the previous frame. So it's important to do the movement and the mouse look first, and then we place the turret, because this depends on where you're looking and where you are, right? Making an FPS game where you play as a moving turret would be awesome. You know, it's possible. You can, you are learning how to make games. So this is maybe this is your first game project, or maybe this is your indie breakout hit. Who knows? The possibilities are endless. I mean, not exactly, but you know, theoretically. All right. Any questions about that? And I guess I should also commit this code in case you want it. Oh, Bastion from Overwatch? Oh, right. All right. Yeah, maybe. Here's an idea. Instead of making a tower defense game, you're gonna make a tower offense game. There you go. That's a golden idea right there. It's just there for the taking. You can have that one. It's on me. It's free. Okay. We don't have a whole lot of time left, right? Shit. We have like almost no time left. Oh boy. Because we're going to 16, right? I actually forgot. Oh yeah, plus 15 minutes because we delayed a little bit. Where's my calendar? It just ran away from me. Okay. Here's a question. We have a few more things that I want to talk about, and we only have about 25 minutes left. Are you okay going a little bit more over time, or how do you feel about that? Like, do any of you really have to go, or is it okay if we go like maybe just a little bit extra? Like, what are the vibes? Because I feel there are a few more things that I really want to talk about. I can't, but I'll watch back later. All right. I want to learn about physics, point, and trajectories. We just did point physics, so this is kind of what point physics is, except the only difference is that we would add gravity to acceleration. So point physics we've already done. Trajectories is kind of a different way to do that. Yeah. But yeah, trajectories is a whole nother topic. So the two things we have left to talk about is value and range remapping and interpolation. And we should probably talk a little bit about graphs and like animating one-dimensional values, I guess. And then trajectories, if you want to. Trajectories are a little bit, can get a little bit complicated and mathy sometimes, but it might be worth talking about. Okay, but interpolation is the most important one, so we're going to do that first. Okay. Okay, yeah. Let's go. Should I just continue, or do you really need a break? So I feel like it might be nice to just continue, since we're low on time and I need to go open a window. Continue at 4 or just do it. Geez. We have two conflicting things. Okay, let's do continue at 4 and then we're gonna do just full steam ahead after that. Or wait, you did? Now you have two conflicting things. What are the votes? Break or not break? Changed my vote. Just have one person wants to break or it's, okay, let's do a break. Let's just go for it. I don't want to stress people out. Okay, let's resume at 1600. Oh, there's a cat. There's a boy. Hello, Simon. He's on the wheel of my chair. That makes me uncomfortable. Be careful, buddy. I haven't checked in a YouTube chat for ages. I don't even know if I have YouTube. It's anywhere. Oh, there it is. Send us toasty emotes later. I don't think I have emotes, but I have lots and lots of pictures of toast. I just Googled toast. That's not how I get to my photos. Let's see. Where are the good toast pictures? I'm gonna post them in the off-topic thread of this course. That's where I'm gonna post the toast pictures. So there's toast drinking water. Here's toast drinking water, but where the tongue is visible. What else? Here's Toast, who found an insect. This is He's got such a face. What a toast. I love him so much. Where's the... I think those might be the most emote worthy pictures. I guess this one is pretty good too. There's another insect in our apartment. Where are the... I'm looking for a specific picture series. Here's salad. This is a good picture of salad. What a boy. He's drinking water. That glass bowl has since been shattered. Toast had a very special day where he ran around trashing various items, and that glass bowl was one of them. Oh, I guess they're back to their beds. They're hanging out over there. Okay, I think that might be all I have time to find before we resume. Oh, actually, this one is very good. This one is very good. I wanted to find this one, and I found it. Hell yeah. It's a good toast. Okay. New Kylo Ren promo pics. Here's a lightsaber toast. Here you go. That could be a poster. Just rotate it, and then you got a poster. Okay, I think you have enough emote material for toast. I think that should do it. Okay. Let's resume. I have my drink. All right. Not a whole lot of reactions this time. Everyone just went home. Immediately. Just went to nap. Okay, good cat reactions. Hell yeah. All right. Okay. Let's talk about interpolation. I think it's time. So we talked a little bit about this earlier, but now we're going to talk about it proper. So there is a very, very, very special function that we use a lot that we call Lerp. So Lerp is short for linear interpolation. All right, as a linear interpolation, this is kind of a fancy way of saying blending along a straight line. That is kind of what that means. Interpolating is just blending between some data points. And so Lerp can be used to blend a lot of different things. And so, for example, you can use Lerp to blend between two positions. Let's say you have a position A over here. Guess we should continue to use lowercase. And then you have a position B over here. And if you imagine a straight line between these two positions, Lerp allows you to get a point along this line. And it allows you to do that using a parameter called a t-value. So if you imagine kind of a percentage from A to B, then this value here is usually called t. And in this case, maybe t is like 0.75-ish, somewhere there. Because it's about 75% along the way from A to B. So if t is 0.5, we would get this point. If t is like here, we would get this point right here. That's what the Lerp function would return. Let's mark that as yellow. And so what Lerp is just a very simple formula. So the final point we get, maybe we should call that P, or maybe V actually, that's going to be useful later. Let's call it V. So for Lerp, it has a very simple formula. So V equals so 1 minus t, oops, wrong color, 1 minus t multiplied by a plus t multiplied by b. And that's it. That is a very simple formula. They're kind of trading off weights. So when t is 0, a is multiplied by 1, because 1 minus 0 is 1. And then we get 0 times b. So when t equals 0, we get a. When t equals 1, we get b. When t is 0.5, we get the point right in between. When t is 0.25, we get the point 25% from a to b. And so this is a very useful function whenever you want to blend from between two things. So this is kind of the math formula for Lerp. Unity also has Lerp built in. There's Lerp is built into many classes, so you're going to find that all over. But this is how you would write it if you want to write the math for it. And Lerp is not just for positions. In this case, we're blending between two coordinates, right? But we can actually just blend between two different numbers as well. You know, if we have the number line, and we have the number 8, and then we have the number 16, then if t equals 0.5, then we're going to get whatever is halfway between those two, which I don't even know what that is. 12? Sounds like it should be 12. I don't even know if it's 12. I think it's 12, yeah. So if t is 0.5, we would get 12 as our return value here. And so Lerp just allows us to blend between basically whatever we want. And so the that's a beautiful emote. I guess it's not technically an emote, but it looks great. All right. And it also allows you to blend between other things. So maybe, what if instead of blending between like the coordinate of A, what if we want to blend from this color to this color? Well, what if we want to do that? Well, we can do that too. And this is something you're going to do in shaders a lot. So shaders deal a lot with color blending and interpolation. So if we interpolate the color, it would look something like this, right? We're blending the color from one color to the other. It's probably should be a little bit smoother than that. I'm trying, okay? So now we are lerping between two different colors. And so I guess in this case, it's basically a lerp where A is just a color and B is also a color, and then we have our t value, right? The percentage. And the t value in this case is just the coordinate along this whole thing, right? And so this is kind of a nice way to just blend between whatever you want. You can blend between positions, you can blend between numbers, you can blend between colors, you can even blend between angles. So if you have some angle A here, some angle B here, you can blend between those too if you want some halfway blend between those. So you can do that. You can blend like rotations, and we used that before. When we did the smoothing, we used a function called slurp, which is spherical linear interpolation, which is also a way to blend rotations using this type of interpolation method. And so this is just a very useful function. You use that a lot. Okay. Did that make sense so far? Should probably organize this a little bit better. I'm guessing that makes sense. We're gonna say that makes sense. Great. Okay. Do you want an example of this, or should we move on? What do you think? Just to see it in action. Example, please. Okay. The scene is getting a little bit cluttered, but that's okay. Lerp test. Wait, did I rename something? Oh, I have locked my selection. All right, Lerp test. There we go. Reloading script stuff. Beautiful. Let's make an A and B things. And on draw gizmos. And then we want the positions of these. There we go. Draw a line from A to B. And then we also want a range from 0 to 1. We're going to call that t. That's just our t value. And then we're going to draw a sphere. Is the transform type actually a matrix? I believe it does contain the same information as a matrix, yes. I don't know if it stores it as if it directly stores it in the matrix. I would guess it does. I would assume the transform contains a matrix 3x4. I would guess. But I could be wrong. But in one way or another, it has to use matrices. I just don't know if it stores them in a matrix. It could be that it just stores the quaternion and the position and the scale, but yeah. All right, and then we want to draw a sphere. So we want to draw the a position that is blended between A and B. So we're going to use Lerp to get our interpolated position. So we're going to do position equals, and then vector3.lerp. And that's a linear interpolation. We're going to blend between A, or from A to B, based on our t value t. And then we're going to draw a sphere at that position. Okay. Let's see if that works. We're going to get a ton of null reference exceptions, and that's okay. So we have A, and we have B. There we go. Assign them there. Oop. There we go. Okay, so we have A and we have B. And now if we drag this slider, we are blending between A and B. And so we can just kind of blend directly between them. If we move A, you can see that the blend is also moving. And so our t value directly controls the percentage from A to B. And so that's the basics of a Lerp. And we can continue doing this with different things. So we can maybe Lerp the color as well. So we can do color. Let's see, color A, and then we do color B. And then we want to change the color of this sphere. And so we can just directly Lerp the color. So color, and then we do color.lerp between, so color A, color B. And then we draw a sphere using that specific color. I guess we can just directly assign it. And there we go. So now if we go back, I believe it's going to be invisible. It is, and that's because our color is fully transparent right now. So if we should bump up our opacity. So maybe we want to set color A to my brand color, and then color B to my other brand color. And so now you see that it's red in the beginning, and then it's fading over to become blue. And so now we are basically using the same Lerp function, but instead of doing it as a position, we're doing it in color space. You can sort of imagine color space as the RGB cube, where each axis corresponds to red, green, and blue. And so we're kind of just blending along a line between 2 points in color space. That's what we're doing here. So we're blending from our red to the blue one. And so this is kind of the basics of Lerp. You interpolate between two values. You have some known start and a known finish, and you want to get some percentage along that, like a blend between those two. Yeah. Does that make sense? How Lerp works? That toast sticker is very good. Okay. All right. Let's see. What do we do next? I have my notes. I need my notes. I can delete a few things. We've done that. We've done Lerp. Right. Okay. So that's Lerp. That is very useful for blending between two values. But then, sometimes, you actually need the opposite. And so this is going to be a bit of a esoteric use case, maybe. Probably not too esoteric. Let's say that you have a an audio source. Like there's an audio source playing somewhere. So there's audio coming out here, and you want to change the volume based on how far away you are. Let's say maybe you want it so that when you're within a certain radius, you want the volume to be at the maximum, right? Like this should be maximum volume. So max here. But at a certain range, you want it to drop off to being inaudible. Okay. And so this is a use case for something called inverse Lerp. So now we basically want to do the opposite. And what do I mean by that? Well, we want a function so that we have the distance. I'm just going to draw that as a line now. So if we can just probably just fade these out a little bit. Now, if you just think about the distance here, we want it so that the volume at a certain distance, I'm going to draw a graph now, so it's kind of like a graph from the side. We want the volume to be 1 here, and then we want it to drop off and then down to 0 over here. Or sorry, other way around. We want it to be 1 over here and 0 over here. So we want this kind of slope shape to it, right? And then if it's inside the maximum range, we want it to stay at 1. And then outside it should be 0. So this is going to be the volume of our audio source. And so it's basically remapping distance to volume? Yes. And so we can do this using the inverse Lerp. And so what do I mean by that? Well, if this is Lerp, just going to copy that, then inverse Lerp is basically the opposite of this. And so the opposite of this is basically we give it A, B, and V, and we want T out of it. So we're swapping T and V. So instead of getting a value between, we supply a value between, and we want to know what is the T value of that point. So we're basically reversing our Lerp function now. And so I'm going to move that here. So this is going to be our inverse Lerp. So by reversing this, we end up with a different formula. So now we want the T value out of this. And so, oh wait, I should do that. What happens if we supply a value that isn't between the 2 points? So Lerp can extrapolate. If you set this T value to 1.5, we're going to get this point over here. So it kind of extends to infinity. But if you're talking about inverse Lerp, there is not really a good inverse Lerp function for vectors. For numbers, it works fine. But for vectors, you'll basically get 3 different T values per axis. So that's what's going to happen with inverse Lerp for vectors. Yeah, so if it's not on the line at all, that's what would happen. You would have 3 separate t values, one for each axis. Okay, so inverse lerp. You can do algebra to shuffle all of this around. But long story short, you are going to get, let's see, it is v minus a divided by b minus a. This is inverse lerp. So this basically does the opposite. Given a start and an end and a value between start and end, where is that in terms of a percentage? And so in our case, the start and the end values are the distances. So we want our a distance to be the maximum range here, right? So that's going to be a. And then b is going to be the minimum range. And then v is going to be the current position of the player, because the volume depends on where we want to measure it, right? So if the player has a position here, then the distance to the player would be our v value, right? And then using the inverse lerp, we can directly figure out the formula for what volume we should have here. What happened to the 1 in v equals 1 minus t times a? Well, you can reformulate this formula in other ways if you want to. So this is equivalent to... so this is equal to a plus t times b minus a. You can do the algebra to like shuffle it around like this, and so it's a little bit easier to see why that is the case here, right? So you can go from this formula, you can reverse it, and then you end up with this, if that makes sense. I can show you the algebra for that if you want to, how to calculate inverse lerp. But I'm guessing you know algebra, or maybe you know algebra. I don't know if you do know algebra. Maybe you don't do that much algebra. Okay, but so so this was our formula, right? And we want to reverse this. And so we can move things around. We can subtract a from this side. So it becomes v minus a. So we're removing a from this side, because we subtract a from both. So then we end up with this. Then the next step is to divide both sides by b minus a. And so we can literally just scoot this down there. And so we divide. Now we don't need the parentheses anymore. And we end up with our inverse lerp function. So that's how you calculate it. And so there you go. Inverse lerp. Is there any term for other popular, more frequently used interpolation curves like sine and stuff? Kind of, yes. Well, it depends on what you mean by interpolation curves. So if you're talking about one-dimensional interpolation curves, you can quite often define functions like this, that kind of smoothes your interpolation to not be linear, but instead have a bit more of a curve to them, right? So maybe you want to have a smooth curve, maybe you want to do like a curve like this or a curve like this. These are called easing functions. And so if you want to read up on easing functions, you can do that. We don't have time to talk about that today. I wanted to talk about them, but we don't have that much time. And so this would be easing functions. So you can apply those directly to your linear values like this. Yeah, so that's inverse Lerp. Okay. And so we do not have a lot of time left. I think we have to cut the official thing short here because we're very over time. Okay. But I could stay for a little bit longer, but I don't want to like keep you for too long. Like, do you have things you need to run away to, or I don't want to like force you to feel stuck. But I could go for a little bit longer if you are okay with that. Personally, I have about 45 minutes left, but I don't think I want to go for that long. I'm pretty tired. It's a very good toast. You're probably ready to be done? Okay. Then I'm just gonna... I haven't been able to talk about Bezier curves. So maybe I'll just briefly mention that, because that's kind of cute. Let's just talk about Bezier curves, and then we're gonna call it a day. No, actually, we have one more function left. Shit, I almost forgot. So there is a combined function. Urge to explain Beziers, yes. So there's a combined function of Lerp and inverse Lerp that is super useful, called a remap. So remap is basically a combination of both, where you're doing both an inverse Lerp and a Lerp. So let's say that not only do you want to get a value from 0 to 1 here, but maybe you want to have specific values here. Like, let's say this is not an audio source. Let's say this is an explosive barrel in a video game, and it's very dangerous, and if you shoot it, it's going to explode. And maybe you want to inflict more damage if you're closer and 0 out here. And so maybe you want a specific damage number here. So maybe not just 1, but maybe 163 is maybe the optimal damage number for your explosive barrel. Then now you kind of have 4 values to deal with. And so remap is actually a combination of Lerp and inverse Lerp. And you can sort of define the remap from we basically have an input value. So it's our A input, and then we have our B input, and then we have our C input, and then we have D, or wait, not input, output. This is our output range. And then D for our output range. And then finally, we're going to get an interpolated and remapped value out of that, or a value we're sending into it. And we call that V before, so let's just call it V. Okay, and so remap, this whole thing is relatively straightforward. It is basically first an inverse Lerp that calculates a t value. So inverse Lerp between the input value of A and the B input value, and then our value over there. So that calculates t. I'm writing code now, not math. And then we want to return lerp between c0 and then d0. And then that we're going to have our t value there. And so this is kind of what remap does. Given an input range, remap this value to the output range, which is very useful. Maybe you have a value between like 6 and 10, and you want to remap it to 100 and 200. Classic use case. So for our exploding barrel, this value right here, this would be C0. That would be the green one. No, sorry, that would be D0. So this one. And then C0 would just be 0. And so we can use a remap to do this whole thing. Is inverse lerp a function in Unity? Yes, inverse lerp exists in Unity. Unity's inverse lerp is clamped by default, I believe. And lerp is as well. So what we actually did here is the unclamped lerp. Just a thing to keep in mind. This basically allows t values outside of 0 to 1. But Unity's lerp function restricts that by default, which I don't like. But yeah, so anyway, remap, super useful function that basically just takes one range, remaps it to another. And again, you can kind of combine this. So maybe you want to make a remap where you want to go from the health values of 0 health to 100 health. Then you want to remap that to a color, right? So you want to change your health bar color depending on how much health you have. Again, that's just a remap. That is an inverse lerp for the percentage of health, and then a lerp to blend the color of the health bar, right? And so that gives you what you want in those cases. So these are super useful. I have done a talk about this before. So if you want to dig super deep into lerp and remap and inverse lerp, I have a talk on my channel. Yeah, so feel free to check that out. Maybe I should link which one it is. Where is it? Okay, here's my talk. Lerp, remap. Okay. All right. And then finally, we're gonna end on Bezier curves because I think they're kind of pretty. So the last thing I want you to know is that Bezier curves are actually based off of lerps, or you can define them entirely using lerps. So you probably use this tool in Photoshop sometimes where you have these like handles, like the vector graphics tools, like this. And then there's like a smooth curve that's like bent based on these handles, right? Something like that. And so this is called a Bezier curve. Specifically, this is the cubic Bezier curve. And this one can actually be entirely defined using lerps. And so the way that works is that if you have a point, or I guess we have 4 points in this case, then we connect them using lines. And then let's say we want to lerp along all 3 of these lines. We're going to lerp at 25%, or maybe 50%. Let's just do 50 because it's easier. So then we get these 3 points, right? But then what if we draw lines between those points? We can do that too, right? And then we lerp along these lines. So now we have 2 more lerps. We're getting lerps here and here. And then we can connect those 2 lines. And then finally, we can lerp on this line, and we end up with this point right here. If you animate this, if you change t from all the way from 0 to 1, this will trace out the cubic Bezier curve. It's a little bit hard to freehand, but so this will actually draw the Bezier curve. And it will look something like this, except better. And so that's really cute. And the thing I really like about this is that it's so easy to remember and also very easy to implement. And so let's just do a quick implementation of the Bezier curve. So we're going to do 2 more points, C and D. We're going to, oops, C and D. Gonna need C, D, C, D. All right, so we're gonna make a function to evaluate a Bezier curve to get a point in it. So vector 3, get Bezier points. And here we're just gonna pass in the vector 3s. And our t value. Okay. All right. And so, like I mentioned before, it's all just lerps. So we do, so we can calculate the values here. Actually, let me rename these because it's easier to use numbers like this. We're just going to call them P0, P1, P2, P3. So we're going to get a new point. We lerp on the first layer of lines. So that's going to be a point we're going to call A. So vector 3 dot lerp between P0, P1 based on our t value. All right, same thing for B and C. We're going to do between P1 and P2, and then P2 and P3. And so this is the first layer of points. These are the red points here that we just defined. So A, B, C are the red points. Then we do 2 more lerps because now we want to blend between A, B, and C. We're going to call this D and E. So we're going to lerp between A and B, and then B and C. And then finally, we're going to return this green point right here. So we want to lerp along this last line, the blue line. So vector 3 dot lerp between D, E, and based on our t value. And that is enough to sample a Bezier point. So instead of drawing a sphere here, we're now going to call get Bezier point. And it's going to be A, B, C, D, and T. Okay. Then we might want to draw some lines from A and B and C and C and D. Okay. Recompile. Then we need to assign our points. And then we can move C and D. And so now, when we pull this slider, you can see that it's tracing out a curve. So we can pull T all the way from 0, all the way to 1, and then it's moving along a curve. And this is the cubic Bezier curve. And so if we move this around, we can do this little S shape. And you can see that it's smoothly moving all the way from A to D. Using this very simple formula, you just lerp until you have a curve, right? That's way simpler than I thought it would be, isn't it, right? It's cool. Yeah, and then if you want to draw Bezier curves, you can use a similar approach. So if we want to draw it, draw the curve, because it might be nice to be able to see it, right? All right. We're going to start at A. I guess it's a vector 3. Get Bezier points. A, B, C, D, and then we need a t value. So we're going to do I divided by detail minus 1. So there we go, t draw. And then we do gizmos dot draw a line from the previous point to the current point. And then we assign the current point to the previous point. Okay. And so then we can see if this works. And now we've drawn a Bezier curve using our gizmos. Isn't that cute? Isn't that neat? And this is also 3D, by the way. So if we rotate our camera, we can just move this out of a single plane into 3D space. So now we have a 3D path. All right, and there you go. That's Bezier curves. And again, we can lerp this, and we're gonna move along the path. This would have been so useful for worms. That's possible. I don't know what you did for your worms assignment. It was an assignment, right? What would happen if you added another vector 3 input, as in another layer of lerps? It would also be a Bezier curve. It would be, then it wouldn't be a cubic Bezier curve, then it would be a quartic Bezier curve. But yeah, you can do that. You can keep adding however many points you want. I have visuals for this that are pretty, rather than just drawing them all the time. And so my next video is all about splines, and the starting point is literally Bezier curves. And so here's the construction of the cubic Bezier curve. You do the lerp on all of these lines, and then finally that traces out the Bezier curve. And so this whole video is a ridiculously deep dive on splines, starting with Bezier curves. But you're asking, can you add more points? Yes. And so here's an example of a dodecic Bezier curve. So we add more points, and then we do the lerp a bonkers number of times, and then we end up with this curve right here. And so yeah, you can make Bezier curves of a higher degree. And so the degree of the curve is a number of points minus 1. So this is the dodecic Bezier curve. Yeah, totally possible. And then this whole video is dedicated to talk about why it's a bad idea to use Bezier curves. It's a very, very, very elaborate, very long video about splines and many different properties. Yep. And you were asking about color space. I actually have that as an example at the end of this video. So here's a color gradient, which is basically just a spline in color space, right? And so here you can see the lines in color space where you have an input t value. So this is the t value here, and then the output is the color that we get out of the spline. And then we can like modify those points in color space, and we end up with a different vibe, a different coloring of our output. Anyway, is this RGB color space though? Yes, in this case, because it's out of scope to dive into other color spaces, and so there's no point in doing that for this video. Okay. All right. I think that might be it for what I wanted to talk about today. We did curves. We ended up doing Bezier curves. We did it. Oh, you were asking if you could do Bezier curves in color space? I did at the end of the Bezier video. I used them to color my Bezier curve in one section. I think I missed a part. I'm not getting 3D lines. Your T draw should be I divided by detail minus 1. So this should be I, right here on this line. When's the video going to be out? I'm not sure. I have so much this week with the lectures and everything. And I have a bunch of other things planned. And so I'm not sure. Ideally within a few weeks, but yeah, somewhere there. The problem is that like it's been really hard to work on it because it's the video is what caused my burnout. And so I always have this like trepidation to come back to it. Okay. Not sure what this is supposed to be. You're drawing it from 0 or the starting point to the current point. So I'm guessing you're missing this line right here. That's what it would look like if you were missing this line. Okay. All right. I think that's going to be it for today. And then we have our, tomorrow, you're going to have time to work on assignments. I'm going to come up with assignments for tomorrow and the day after that. I'm going to be available for mentorship tomorrow. So I'm not going to do lectures. No trajectory. I was looking forward to it. I mean, we have extra time. And so we could do trajectories tomorrow, or we could do that on Friday. There is time to do it. It's just a matter of like what we would rather talk about. Are dropping assignments today or tomorrow? Ideally not today. Every time I stream, I get a really bad headache afterwards, and so sometimes it's hard for me to focus on things. Okay, here's an idea. Yeah, I was gonna say what Carolina is saying. We could do trajectories in the morning, and then that'll take however long it's gonna take, and then we do assignments after that. Okay, yeah, we can do trajectories tomorrow. I think that's a good idea, just so you don't miss out on that. Okay, I can probably think of a few assignments today. If I will, they're going to be in the document. If you're on YouTube, they're going to be in the description. Yeah, I'll let you know. I'll ping you in the server if I do assignments. Otherwise, I'm just going to improvise them tomorrow, like after the first lecture. Okay. Yeah, I think that's it. Thank you all for joining. Any final questions before we go? Before I go? I don't know where you're going. Headache sounds like eye strain. I don't get this headache unless I'm streaming. If I can sit by my computer all day and I'm gonna be fine, but if I'm streaming, I get a headache. I think it's related to talking. I think when I talk this much and for so long, I think I might be tensing my neck or something, and I don't know. I think it's just because of the talking. Because if I stream without talking, I've had a few streams where I just do music, I don't get this headache. So I think it's either because I'm talking so much or because I'm, I don't know, social anxiety, pressure, I don't know. Who knows? Okay. Canonical end of our lecture. Well, it's the kind of the end of my planned lecture, but I mean, we're gonna do trajectories tomorrow. Sort of unplanned lecture. You know what? Let's do it at 9 o'clock. I'm gonna do it. Just 9 o'clock. You're gonna get up early, and so you're gonna try to fix your sleep schedule. There you go. I'm being an asshole. So we're gonna do 9 tomorrow as well. And yeah, trajectories tomorrow at 9, and then you're gonna work on assignments. I'm gonna be available all day. On Thursday, I'm not gonna be available, or I mean, I might be intermittently. I just don't have any planned time to be available. And the Friday is going to be reserved for the last kind of more fun or esoteric topics that you really want to talk about. I think Udit was going to organize a list of topics that you could vote on. I don't know how you want to do voting or how that's going to work, but it would be great if you could set up some sort of list of topics and people can vote on topics and suggest topics, and then just let me know what the results are on Friday morning, I suppose, and then I'll talk about whatever. Okay, it's going to be a little bit prioritized based on my knowledge and the usefulness of it or how interesting it is. Yeah, so some things might not be something that I'm super well versed in, and so I shouldn't be the one talking about it. Okay. And I think that's it. Thank you all for joining. Hope this was educational. Sorry for going overtime. Hope it wasn't too much. And yeah, I'm guessing YouTube chat is doing great as usual. All right. YouTube chat, it seems fine. No burning questions. Okay. Yeah, thanks for those of you on YouTube who joined. Sorry for not interacting with all of you, but this is primarily for my FutureGames students. They have teacher privilege. I'm going to focus on those students. But I appreciate y'all in YouTube chat anyway. Yeah. All right. Any last things before I close the stream? Shit, I'm gonna have to cut the stream very quickly. Otherwise I'm gonna hit the 4-hour mark and we're not gonna get subtitles in the video. How do you not get tired talking for 6 hours? I do get tired talking for 6 hours. That's the answer. Okay. Thank you all for joining. And I will see you all tomorrow at 9. We're gonna talk about trajectories. Bye everyone.